Hello and welcome to GE's STATCOM webinar. Today we'll be looking at how STATCOM can solve dynamic grid problems. Let's first start by introducing ourselves. My name is Louis Nivelo. I'm a sales director. I'm located in Tampere, Finland, where our Center of Excellence for SVC and STATCOM is located. I've been with GE for 10 years now. I have expertise and experience in substation, HVDC, and FACS, mainly in tendering and sales activities. I hold a Master of Science in Electronics and Signal Processing. Nowadays, I'm leading sales and tendering for Europe, Africa, Middle East, Asia, and Pacific. And here is Jussi.
Thank you, Louis. My name is Jussi Pöyhönen. I'm working for GE FACS System Design, supporting tendering, R&D, and project execution. I'm providing transmission system analysis and grid interconnection studies to understand customer needs and optimize compensation system solutions.
Thanks, Jussi. So here is today's agenda. We will first start by listing today's grid challenges, and then we will see how FACS devices can support grid issues. We will then look at STATCOM operation principle, and then we will go through one simulation case. Let's see what are today's grid challenges. Globally, the utility environment is becoming more complex and facing new challenges, such as increasing demand for electricity, need for security of supply, or even integration of renewables. Hence, utilities are looking for cost-effective AC and DC solutions that can improve the quality, reliability, and stability of the grid. How these challenges impact on the grid? These challenges can make the power flow stability more complex for network operator to manage, but also the increase in demand combined with aging infrastructure can cause several issues like grid voltage fluctuation, stability issue, unbalanced load, or even power oscillation, all of which can impact on the power quality and on the power transferability of the transmission line. All these grid issues can be tackled with FACS devices. Let's first start by defining what is a FACS device. A FACS solution is a power electronics device that can dynamically provide reactive power on an AC network in order to support the voltage along the transmission line, hence improving the efficiency and reliability of an existing or of a new AC transmission line. There are two types of FACS device. First, shunt compensation device like synchronous condensers, SVC, or STATCOM. This equipment, they are connected in parallel to the grid. We have also series compensation device like FSC and TCSC. These equipment are connected in series to the grid. What are the attributes of a FACS solution? A FACS solution is a solution having a controllable output and is a solution that can respond quickly and in a smooth manner to grid changing conditions. It also offers a broad spectrum of performance like transient stability. It can also provide an increase in the power transfer of a line. It can also provide power escalation damping, and eventually it prevents the voltage from collapsing. Here is GE Grid Solution FACS portfolio. GE has FACS devices in its portfolio. Let's first start with series compensation. GE is the market leader in series compensation. GE has delivered over 230 systems in the world, and GE has been developing and is still using different technologies based on fuseless capacitors or externally fused capacitor or even internally fused capacitor. Now, synchronous condensers. GE is also the market leader in synchronous condensers. GE has been delivering nearly 200 machines worldwide. GE has the broadest portfolio of machines in the industry, ranging from small machines from 15 to 100 MVR up to big machines close to 300 MVR. Let's look at now SVC. GE is proposing classic SVC like others in the market, but GE is also proposing its patented SVC design called main reactor design. GE provides its own control system called ADC and is also manufacturing its own thyristor valve called ATV. These two equipment, control system and thyristor valves, are manufactured in GE's Center of Excellence for SVC in STATCOM, located in Tampere, Finland. And GE has over 60 years of experience in SVC and has delivered 380 SVC worldwide. STATCOM. GE has been a pioneer in STATCOM, has been developing several STATCOM technologies based on GTO, 3-level STATCOM, and GE is now using its latest technology called MMC, which is shared with our colleagues from HVDC. The control system implemented on STATCOM is actually the same platform as used on the SVC. And GE has been delivering 20 STATCOM worldwide in 14 different countries. With that portfolio, GE trusts to have the most complete portfolio in the industry.
Thank you, Louis. Increasing renewable power production and power electronics interconnecting transmission systems requires means for reliable voltage regulation. STATCOM systems are to support transmission system voltage, to control reactive power balance, and to dampen adverse effects of network transients. They provide voltage control and fault ride-through support to integrate renewables into transmission systems. Today, we are focusing on STATCOM for utility applications, where STATCOM system is connected into transmission system between generation and end users. It is providing reactive current into electric transmission system to control voltage and boost network stability and reliability. STATCOM system current is controlled continuously to respond instantly any change in generation or loading or in transient conditions, switching events or network faults.
When power is generated, it is measured in megavolt amps, or MVA. MVA is made up of two components: megawatts, otherwise known as real power, and megavars, or reactive power. In an ideal power system, the power required by the end users, the megawatts, makes up 100% of the generated power. Little to no reactive power is required in the system. In the real world, however, inductive devices such as motors and transformers exist on the system. These devices consume reactive power. The power utility must generate reactive power and send it to the end user. This consumes valuable limited transmission capacity, lowers the transmission voltage profile, and reduces efficiency significantly, increasing generation and transmission costs. Fixed capacitor banks can supply the reactive power needs of the load devices and reduce the load on the generators. However, a dynamic device is needed to rapidly respond to the ever-changing conditions of the transmission network. A static synchronous compensator, or STATCOM, is a reactive power source that uses complex control systems and IGBT switches to dynamically control reactive power output. STATCOMs can significantly boost the stability and reliability of the power transmission network by continuously regulating the voltage on the transmission line. This results in a power transmission superhighway capable of transmitting much greater amounts of real power over the same infrastructure. When a disturbance occurs, such as a power system fault, the STATCOM reacts rapidly by increasing output. This improves the real power transmitted to the consumer, thus minimizing the effects of the fault. Once the fault is cleared, load reactive devices simultaneously come back online and cause significant voltage sag. The STATCOM again responds rapidly, dynamically supplying the necessary reactive power to boost voltage and prevent undervoltage conditions or complete loss of power. With STATCOM systems, grid operators gain fast, accurate control of the reactive power network, all with minimal infrastructure investment and low environmental impact.
GE's utility-grade STATCOM solution is a custom designed for electric transmission systems. Modern multimodular converter topology is reducing STATCOM system losses while the response time is very fast. It provides grid operators with reactive power compensation and improved undervoltage performance, low harmonic current content, and a smaller footprint than traditional SVC solutions. A shunt-connected STATCOM is able to generate capacitive or inductive current independently of the transmission system voltage. This presentation will briefly cover STATCOM operation principle, operation characteristics, namely voltage current capability for STATCOM rating, single line diagram, where we can see the key components of the STATCOM system, voltage source converter valve construction, and the heart of the STATCOM system, the valve submodule. Now, let's concentrate on STATCOM system operation.
A modern STATCOM is a shunt-connected device that is comprised of an IGBT-based voltage source converter, connected to the transmission grid via series-connected phase reactors, and a step-up power transformer. A STATCOM can act as an inductive device, absorbing reactive power from the grid, or a capacitive device, producing reactive power to the grid. The basic operating principle of a STATCOM is that it produces a voltage waveform in sync with the transmission system voltage. When in the inductive mode, the voltage waveform generated by the STATCOM is smaller in magnitude than the grid voltage, thereby absorbing inductive reactive power from the network. When in the capacitive mode, the voltage waveform generated by the STATCOM is larger in magnitude than the grid voltage, thereby generating reactive power to the grid. So how does the STATCOM generate these waveforms that control the reactive power output? The basic building block of the STATCOM is the valve submodule. Each submodule consists of a pre-charged DC capacitor, a high-speed switch, and electronic boards for protection and communications. Typically, there are 5 to 8 submodules stacked together to form one valve module. Several modules connected together form a complete valve for one phase of the STATCOM. These are generally stacked 3 high to form a 3-phase system. The high-speed switch that is in each submodule is actually a set of 4 power electronic devices called insulated gate bipolar transistors, or IGBTs. These 4 IGBTs are arranged and operated in a configuration that produces a positive, negative, bypassed, or blocked state. Starting in the blocked state, the submodule output voltage is 0. Turning on IGBTs 1 and 4 results in a positive output from the submodule, creating a positive step in the waveform. Turning on 1 and 3 or 2 and 4, the submodule is bypassed and our output returns to 0. Turning on IGBTs 2 and 3 results in a negative output from the submodule and a negative step in the waveform. Adding more submodules in what is called a modular multi-level converter configuration, we can generate a smoother sinusoidal waveform of the desired amplitude. To achieve this, the control system sequentially turns on each submodule to sinusoidally grow the total voltage of the converter in the positive half cycle until the peak. It then turns them all back off sequentially to bring the waveform back to 0. The control system then changes the IGBT configuration to generate the negative half cycle and turns on each submodule sequentially as before until the required negative amplitude is reached, and then turns those all back off again. One full sequence produces one complete cycle of a sinusoidal voltage waveform. By adding even more modules, we are able to achieve a smoother waveform closely matching the system. Stacking the modules 3 high, we can now produce a complete waveform for each phase of the 3-phase system. The sophistication of the STATCOM is that it is continually monitoring the always changing system voltage to maintain its output relative to the changing input. Simultaneously, the STATCOM is rapidly providing either inductive compensation or capacitive compensation when required by the system. This complete process allows total control over system compensation and helps to maintain grid stability and boost efficiency.
Steady-state rating determines step-down transformer rating and STATCOM system voltage. Overvoltage conditions effects on valve rating and number of desired series-connected valve submodules. Undervoltage characteristics for how long and how much reactive power support is needed in several voltage dips. Basically, STATCOM system rating is based on these operation points for desired reactive current into the transmission system. This includes transformer selection, VSC valve rating, number of VSC branches, and other possible reactive power sources. In some cases, it might be efficient to expand STATCOM system with thyristor switch elements. They are providing reactive current with rapid response, while voltage source converter is balancing switching of thyristor switch elements. This way, harmonic current contribution in continuous operation is minimal. As thyristor switch elements, namely capacitors and reactors, output power is proportional to the square of the network voltage. Those can be designed efficiently to support system in under or over voltage conditions. In the single line diagram for a simple STATCOM system, we can see step-down transformer to match desired power rating, selecting appropriate voltage ratio and short circuit impedance. Delta connected VSC branch with CTs and DC current transducers, and phase reactor for VSC current control and short circuit current limitation, and pre-charge circuit to limit inrush current in STATCOM system energization. Other key equipments are auxiliary power supply, overvoltage protections, voltage measurements, disconnectors, earthing switches, and breakers. GE STATCOM VSC valve is based on large-scale HVDC valve design principles and standards, utilizing the most advanced multimodular converter architecture with system redundancy through the valve, cooling system, control and protection system, and passive optical network communication system. A number of series-connected valve submodules form a single-phase valve, and then again three-phase valve construction combines single-phase valves in separate tires to match desired performance. VSC valve is open rack structure that facilitates a safe and clean maintenance environment, including individual access to control cards, DC capacitors, and rechargeable bypass switches. Heart of the STATCOM system is a full bridge valve submodule. It has essential equipment and functions for accurate and reliable operation. Redundant valve submodules included in the VSC valve provide failure-safe operation in case of IGBT or other internal failure within valve submodule. It has essential self-diagnostics and protection functions, switch to bypass faulted valve submodule, and have continuous operation for the STATCOM system with the remaining valve submodules. Rapid discharge circuit limits voltage increase in case of short-term overvoltage. Balance and bleed resistor for DC link balancing in valve blocking operation and discharging DC link for safe operation after shutdown. DC capacitor protections include pressure relief switch and valve to limit flammable gas and risk of damaging. Now we will take a look into the brains of the STATCOM system. The GE Advanced Digital Control System provides industry-leading tools to design, simulate, test, and deploy the STATCOM control system software. There is interface between system operator, utility grid, and STATCOM system equipment and power electronics. It serves completely redundant control system and communication arrangement. Modular real-time VPX-based control system for long life cycle and reliable operation based on military-grade components. You can see control, field I/O, and HMI cubicles on the left side picture. Let's take a look now for network fault scenario Louis promised. Worst case single-phase fault occurs right next to our STATCOM system in transmission network. Nearby single phase to ground fault appears, as seen in top left corner. STATCOM has immediate response. Initially, STATCOM has produced nominal positive sequence current into the network while fault appears. We can see in the next picture that there is unbalanced current within the VSC delta connection. However, STATCOM star currents in the third graph are well balanced, since STATCOM control system responds, limiting positive sequence reference and circulating current inside VSC delta connection, the fourth graph. In the second line, starting from left side, we can see this way DC link voltages are well balanced in all three phases. STATCOM current to transmission system is purely positive sequence current to support network voltage balance. Valve submodules DC link voltages are maintained on safe levels for continuous operation and for rapid response for any voltage transient in the network. After fault recovery, STATCOM returns to supply pre-fault current into the electric power system. As a summary, GE's modular multi-level STATCOM solution is custom-tailored to fit customers' requirements. STATCOM provides a more compact footprint compared to traditional SVCs. Robust design of the VSC valve and valve submodule leverages the high performance from HVDC applications. Controls based on state-of-the-art design principles and utilizing multi-sourced military-graded components. Thank you all for watching this webinar presentation.